Welcome to our second help video over 8-10 class notes. In our first video, we took a look at active metals replacing less active metals. In our second video, we're going to be looking at a second type of single displacement reaction. This is where active metals replace hydrogen ions in solution. Remember, acids dissociate in solution, where the hydrogen ion breaks off the acid and floats around as H+. It's looking for a pair of electrons on a base, but we have a hydrogen ion. Acids kick off the hydrogen ion. In this particular reaction, active metals will try to force the hydrogen ion to take electrons. Let's see how this actually looks on our activity series chart. So right here, we have hydrogen on our activity series. Any of the metals above the hydrogen ion, any of the elements or metals above the hydrogen ion can force the hydrogen ion to take electrons. Now, these metals up here, in this group right here, can not only force out the hydrogen ion, but they can actually force hydrogen out of solution on a water molecule. So they can actually replace hydrogen on a water molecule. These metals right here, magnesium, aluminum, zinc, and chromium, they can force hydrogen ion out of solution, and they can force hydrogen off of a water molecule if the water molecule has been heated up into a gas where it becomes steam. These metals right here cannot force hydrogen off a water molecule, but they can force the hydrogen ion out of solution. So let's take a look at an example reaction. Right here, in our first example, they're dropping magnesium into a solution containing hydrochloric acid. Well, can magnesium replace the hydrogen ion when hydrochloric acid dissociates into the hydrogen ion and the chloride ion? Let's take a look at the activity series. Here's magnesium right up here. There's hydrogen right down there. So yes, magnesium can force the hydrogen ion out of solution. Let's take a look at how that would look on a drawing. So here is HCl aqueous. HCl aqueous means that H pluses have been pulled apart, as we see here, and Cl minuses are left floating around. So there's the H pluses, there's the Cl minuses, and we would need two of those acid molecules to dissociate. Why? Because we're dropping magnesium in there. Magnesium is a member of family Roman 2. Group 2, it has 2 valence electrons to get rid of. So it will need 2 hydrogen ions to force those electrons onto, because each hydrogen ion can only take 1 electron. What will happen? Let's take a look. Here's before the reaction. We're dropping magnesium in. Here's magnesium now. This is the reaction taking place. There's magnesium. Magnesium will force 1 electron onto this H plus and 1 electron onto this H plus. After the reaction, that will leave us with Mg2 plus. And then after the reaction, we'll have 2 hydrogen atoms floating around, each with electron. Well, what will those atoms do? Those atoms will share 1 electron with each other to form a single bond so that they can get satisfying the duet rule, because hydrogen needs 2. So each hydrogen will share 1, and we will end up having the gaseous H2 molecule go out of solution into the air. That is why when we looked on the activity series, they had H2, because when you force the hydrogen ion out of solution by giving hydrogen atoms an electron, they will join up to form the H2 molecule. So that's why H2 on this right side is shown as a gas. The 2 H pluses in this container, the 2 H pluses took an electron, each having a total of 1. They share that 1 and form the hydrogen molecule. How do we write that in ionic form? Well, here we go. Ionic form, where they want you to write what's happening to the ions. So when the reaction, right before the reaction happens, we have Mg solid with 2 electrons. We have 2 H pluses floating around in aqueous, and we have 2 Cl minuses floating around. After the reaction, we have Mg2 plus. There it is. After the reaction, we still have the two Cl minuses. There they are. And now we have H2 gas. So the ionic equation is showing what is happening overall in these two containers. Who didn't change? That's the spectator ion. The chloride ion did not change. We have Cl minuses in all three of those containers. The spectator ion is Cl minus. The net ionic equation wants us to just show which ones changed. So we take the one that didn't change, the chloride ion, we could cross it out or get rid of it, and now we have the net ionic. The net ionic is we started with magnesium metal, and when we were done, we had the magnesium ion floating around. There it is, magnesium metal, magnesium ion, Mg2 plus. Before the reaction, we had two H pluses floating around. There they are. After the reaction, we had H2 gas. There it is. So H2 went from being H plus to H2 gas. It changed. So when we do the net ionic, we just take a look at which ones didn't or did change. We get rid of the one that didn't change. Let's move on to the reaction we mentioned briefly already. The very active metals can actually replace hydrogen on the water molecule. They can force hydrogens on a water molecule to take electrons. Which metals can do that? These right up here at the top. They can displace hydrogen both from acid and from liquid water. That L there means liquid water. They can also do it to steam. These metals can only replace hydrogens from steam. So looking at our fourth example here, we're dropping potassium, solid potassium metal, into a solution that's containing water. Can those Ks kick off the H's? Can Ks kick off a single H from a water molecule? Let's go back and look on our activity series. Here's our activity series. Yep, K is in the group of metals, the red ones, that can displace hydrogen, a hydrogen atom, from the water molecule. That's all they're going to do. H2O is really HOH. And what those potassiums are able to do is kick off the H from an HOH. And that's what we're looking at right here. Can the Ks kick an H off? Yes, they can. If we pull an H off a water molecule, we're left with one H and one O. That's OH. And we would have K with it now, because the K displaced an H from HOH. And what are we left with? Well, the H's are going to break off the water molecule. With their electrons, they're going to join up as H2. Another way of looking at the same reaction, we're dropping in K. Water is HOH. So all I did was write water as H with the hydroxide ion OH. So Ks are strong enough to replace the H's. So instead of having an H there, the Ks will be on the water. Instead of being HOH, it'll be KOH. The hydroxide ion is 1 minus. The potassium ion K is in family Roman 1, group 1. They have 1 valence electron, so they will become 1 plus. So we would end up with 1 plus and 1 minus crisscross. What happens to the H's that break off the water molecule? They join up to form, as they did in this reaction right here, the H's will join up to form the hydrogen molecule. So let's take a look at a picture. What would this look like in a picture? The ionic equation. We're dropping in Ks. There's the Ks with their 1 valence electron. There's potassium, K, with its 1 valence electron. Here's the water molecule, HOH. Here's a water molecule, HOH. What's going to happen? Well, these Ks are going to force their electrons onto the H. So there's K forcing their electrons onto the H. What happens to H's electrons? They stay with the hydroxide ion. There's OH minus. So hydrogen leaves its electron on the OH and is forced to take K's electron. So now we have K, who gave its electrons to the H's. When K loses its electron, it becomes K plus. There's the hydroxide ions that were left after the H broke off. And what happens to these two H's? They end up joining Each puts in an electron to make a single bond, which will end up giving hydrogen the 2 electrons it needs to satisfy the duet rule, and it will come out of the solution as hydrogen gas molecule. So there's our ionic. First container, 2 Ks, 2 HOHs. There's the 2 Ks, there's the 2 OHs. What happens? The K gives their electrons to these 2 H's right here and becomes K+. There's the K pluses. After the H's are forced off there, we're left with the 2 OH minuses. There they are. And then the H2s join up to form hydrogen gas. That is the ionic equation. We really don't have a net ionic because here we ended up with everything kind of changing. So there's no spectator ion in this really. Example 5. Will barium be able to replace hydrogens on a water molecule? Let's take a look at the activity series. Here's barium. It is far above the H's. So yes, barium can replace it. So let's take a look at the equation. How would that equation look? Barium is able to replace the H's. Really, we could write this as HOH. Barium will replace the H, leaving behind the OH. Where do I get the formula BaOH 2 times? Well, barium is in family Roman 2, group 2. It has 2 valence electrons, so it will become 2+. So the 2 from barium goes down here. The hydroxide ion, if you remember, is 1-. It would crisscross right there. So we would end up with BaOH2. That would mean 2 hydrogens would be replaced. We'd end up with H2. Every time in the single displacement reaction where active metals replace hydrogens, we end up with H2. There's our H2. Let's take a look at our balancing. We have 2 H2s coming off. We have 2 H's that have stayed with the hydroxide ion. That's 4 total H's, so we would need a 2 in front of the H2O to balance it. That gives us our 4 H's. It also gives us the 2 O's that we have on the hydroxide ion. So that is example 5, barium replacing H. The H's break off, leaving behind OH that stays with the barium. Those OHs would be floating around in solution. We had to write a balance reaction here. We didn't have to draw it. So we've taken care of example number 5. And that is the end of this video where we talked about the second type of single displacement reaction where active metals replace hydrogen ions. And we looked at the third type where active metals can replace hydrogen on a water molecule. We'll take a look at our fourth type of single displacement reaction on our next video. That is where halogens, active halogens, will replace less active halogens in solution.